Okay, so today we're going to look at creating equations for rational expressions. And yeah, so that's going to be mainly and transformations. That's what it was rational expressions. So you'll notice in your notes a few slides here. We're actually going to skip these. We're not going to worry about them. If you see any questions in your notes where you're given a graph and you need to draw the rational for that graph, or if you're given a rational graph and you have to draw the original graph, the reciprocal of it, you can skip those as well. So we're actually going to just start with transformations. So with transformations, okay, the same rules apply as every other transformations we've done. So if my original graph was 1 over x, okay, and then I ended up with a graph of 1 over x minus 3, I'm going to have a vertical translation 3 units down. So I'm going to be translating my graph 3 units down. If you were to type this in your calculator and graph it, you would notice that you end up with a graph that looks something like this. I want to draw that. It didn't work very well. I want to draw that to that vertical asymptote. Okay, so what you should notice is that your horizontal asymptote, which used to be at y equals 0 on the original graph, moved down to y equals -3 on your new graph. Okay, so our next equation here, and this one's a little trickier to notice. Okay, you actually end up, and I'm going to kind of show you something. This is the same as this. Right? So if we were to times that 2 on the outside instead of writing it in the numerator, that would actually be the same thing. But in this format, it might be easier, okay, to guess or to figure out that 2 actually shows you a vertical stretch. So I know I have a vertical stretch of 2 along the x-axis. Because my x was replaced with x minus 3, I am going to translate my graph 3 units to the right. And because I have that plus 2 there, I'm going to move 2 units up. And that 2 you can't really see on the bottom of the screen there, so 2 units up. Okay, so if you graph this, you should notice that your original graph had a vertical asymptote at 0. My new graph is going to have a vertical asymptote at 3 because I moved 3 units to the right. My original graph had a horizontal asymptote at 0. My new graph is going to have a horizontal asymptote at 2 because my horizontal asymptote moved 2 units up. And then from here I can actually graph this. So it's going to approach that vertical, I wanted to pick a different color, purple. That vertical asymptote towards infinity and the horizontal asymptote towards infinity. So it looks something like that. So you can see that our transformations did in fact affect those asymptotes. Okay, so it says find the following without a calculator. So let's actually start off by factoring this expression. So what two numbers multiply to give me -8 and add to give me +2? -4 and +2. So that would be my rational function in factored form. So now let's see if we can figure out the answers to these little bullets without graphing. So would this have a horizontal asymptote? The degree of the numerator is larger than the degree of the denominator. So if you go back into your notes, you will see that no, it does not have a horizontal asymptote. Does it have a vertical asymptote? Yes. Okay, because I do have a factor on the denominator that does not cancel out. So my vertical asymptote would be x equals 1. Does it have a y-intercept? Okay, and at this point you could graph it if you want to. Okay, the y-intercept actually ends up just being my two constants divided. So -8 divided by -1 gives me +8. So it does have a y-intercept at +8, but you could check that graphing it. The x-intercept, so this is pretty important. I want you to pay attention to this. So the x-intercept are any factors in your numerator that didn't cancel out. So this would actually have an x-intercept at 4 and actually this is supposed to be x plus 4 and x minus 2. Oh, good thing I caught that. There we go. So it ends up having an x-intercept at -4 and +2. There we go. That looks better. Oh dear. -4 and +2. Okay, and then from here I'm going to graph this. So let's draw that asymptote at x equals 1. This graph is going to look pretty funky here, and I'm going to have an x-intercept at 2 and -4. It looks something like that. It actually does have a slant asymptote, which is why it looks like this, but we don't need to worry about that in 30-1. I think you cover that in calculus, but not in 30-1 math. Okay. So it says determine the equation of a rational function with each set of characteristics and then draw the graph. So we know we have vertical asymptotes at -2 and +4. So let's start off by writing the factors of those asymptotes on our denominator. So I have x plus 2 and x minus 4. I have x-intercepts at -3 and +5, so I'm going to write the factors of those x-intercepts in the numerator. So I have x plus 3 and x minus 5. There are no holes in the graph, so there shouldn't be any common factors between the numerator and denominator. And there is a horizontal asymptote at 1, which makes sense because if I were to expand this out, I'd end up with a degree of x squared on both the numerator and denominator, okay, which would give me a horizontal asymptote at 1. So now let's try to draw this. So I have an x-intercept at -3, so let's draw that out, and +5. Let's draw all of our asymptotes. We have an asymptote at -2. There we go. And an asymptote at +4. And a horizontal asymptote at +1. Yay! There we go. Okay, so if you were to draw this, it would look like this. It's approaching that, and you could also just graph this in your graphing calculator at this point as well. That's probably your best bet. So you will end up with a graph that looks something like that. Okay, so the next step is we're actually going to be given a graph now and have to figure out the equation. So let's start off by looking where our vertical asymptotes are. So we have a vertical asymptote at -4. So that means I should have x plus 4 as a factor in my denominator. And I also have a vertical asymptote at +2, which means I should have x minus 2 as a factor on my numerator. Okay, so you also have an x-intercept at 1, so you're going to have a factor of x plus 1 on your numerator. Perfect, so this should be my function, and it's great because you can actually graph it on your graphing calculator and make sure it matches the picture. I am going to get you to pay attention to one more little detail here, which is the horizontal asymptote. So you might look at this and say, hey, there's no horizontal asymptote because there's no point that the graph doesn't cross. But actually, there still is a horizontal asymptote at 0. Because if you go back to those rules, when the degree of the denominator is larger than the degree of the numerator, there is a horizontal asymptote at 0. This is just one of those rare cases where the graph does in fact cross that horizontal asymptote. But when you look at the right and left tails of this graph, the graph is approaching that x-axis towards infinity, which is why it is a vertical or horizontal asymptote. All right, so our next graph here, the first thing I notice is that hole in the graph. So a hole in a graph means that the x value of that hole in the graph should be a factor on both the numerator and denominator. So the x value is 1, 2, -3. So that means I should have x plus 3 on both the numerator and the denominator. Okay, and then the other thing I will notice is I do have an x-intercept here at x, 0, so I will have a factor of x. And I have a vertical asymptote at -2, which means I will have a factor of x plus 2 on the denominator. Okay, and I am going to actually get you to pay attention to one more thing with this question. With rational expressions, it's similar to polynomial expressions in the fact that you could have an a value in front. So they could give you a point on the graph, just like we did with polynomials to find that a value. In this case, they actually give us the point of discontinuity, and that can help us as well. So if you were to substitute -3, or sorry, you'd have to cross the x plus 3's out first. If you were to substitute -3 in for x, you'd end up with -3 over -3 plus 2. And if you look at the y value in your point of discontinuity, it is at +3. So then I end up with -3a over -1 equals +3. So I know my a value is 1. So this graph, you don't have to worry about an a value. But you can actually use the point of discontinuity to help you find an a value if you needed one. All right, let's keep looking at equations here. So in this graph, I actually end up having, there's a couple different answers for this graph. So I have 2 points of discontinuity at -2, which means I need a factor of x plus 2 on both my numerator and denominator. And I also have a point of discontinuity at -6, which means I need an x plus 6 on both my numerator and denominator. Okay, so really if I cancel everything out and I would end up with 1, right, with those points of discontinuity. So to end up with a 7, I would need an a value of 7, because notice how the line, okay, is at y equals 7. That's where the 7 comes from. So then my graph would just be y equals 7 times x plus 2 over x plus 6. The other solution you could have had for this graph is you could have started the same way. Okay, and written out all those holes in the graph, those points of discontinuity. And then you could actually, because anything divided by itself is 1, you could think of vertical translations, and you could move this graph up 6 units to end up at the 7. So both of these equations would actually end up giving us the same rational function here. Okay, so let's keep looking here at the next question. So I'm going to start off again with my point of discontinuity. So the x value is 1, 2, 3, 4, -4. So that means I should have a factor of x plus 4 on the numerator as well as the denominator. I have an x-intercept at -3, which means I should have a factor of x plus 3 on the numerator. Okay, oh, and I almost missed this last point hole in the graph, so that is at an x value of 6. So I should have x minus 6 on both the numerator and the denominator. Okay, and then you could try to find an a value here. I'm going to use the y-intercept this time. So when x is 0, y is 3. because remember, you can't just assume the a value is 1 all the time. You do need to double check it. So I'm going to substitute 3 in for a, substitute 0 in for x, so I end up with 4 times 3 times negative 6 all over 4 times negative 6. Okay, and I'm running out of room, so I'm going to move it up here. So that would end up giving me 3 equals a times negative 72 all over negative 24. Okay, and then negative 72 divided by negative 24 is actually, in fact, 3. So then my a value in this case is 1. So I don't have to worry about it. So then this would be my rational expression. All right, let's look at a couple diploma questions before we end today. So the first one says the function f at x equals x minus 1 over x squared plus x minus 2. Which of the statements is true? So I'm going to start off by just factoring this. So two numbers that multiply to give me negative 2 and add to give me positive 1 are x plus 2 and x minus 1. So the x minus 1's cancel out, which just leaves me with f at x equals 1 over x plus 2. So it says the point of discontinuity is at 1 and 1 over 3. We can double check that. So we do know, in fact, that the x value of that point of discontinuity would be at 1. If I substitute that 1 into whatever is left over, I'd have 1 over 1 plus 2, which would in fact give me 1 over 3. So that is true. So then A ends up being the correct answer right away there. All right, last question. The graph of the function below can be expressed by the form f at x equals ax over x squared plus bx plus c, where f at 2 equals negative 1. All right, so let's see if we can come up with the function. So notice how your x-intercept is at 0. That's why you have the x in the numerator. And then my vertical asymptotes are at negative 4, which means I'll have a factor of x plus 4. And positive 5, which means I'll have a factor of x minus 5 on my denominator. So they did give us a point on the graph, and we're going to use that point on the graph to help us find the a value, just like we did with polynomial functions. So we're going to substitute it in. So when y is negative 1, x is 2, so then I end up with negative 1 equals 2a. 2 plus 4 gives me 6, times 2 minus 5 is negative 3, so I end up with negative 18. Cross multiply, negative 1 times negative 18 is positive 18, equals 2a, so then that means a equals 9. All right, it does want it in this form. So now I'm going to go back to this equation, substitute 9 in, but notice how your denominator is expanded. So I do need to expand that denominator out. So I'll end up with x times x is x squared. X times negative 5 is negative 5x. Plus 4x gives me negative 1x minus 20. All right, so then my a value would be 9, my b value is negative 1, and my c value is negative 20.